Good afternoon. My name is Stefan Johansson. I work at Oracle in the Java Platform Group with a focus on garbage collection. A few years ago, a big media streaming company decided to do some really big changes to their internal infrastructure. They decided to upgrade from JDK 8 to JDK 17. This is not a small task, and the work and testing going into this should not be neglected. But the return on this investment was really big, and the benefits they saw were significant. We will come back to this company a bit later in this presentation, but now I want to welcome you to Garbage Collection in Java, the performance benefits of upgrading. I have two goals with this presentation. First, I want to give you a better understanding of garbage collection in general to help you choose the right garbage collector for your use cases. Then I want to focus on showing you the performance benefits of using a more recent release of the Java platform. To cover this presentation is basically divided into two parts. So let's get into the garbage collection primer. Garbage collection is a key feature of the Java platform, allowing you as users to focus on solving your problems rather than thinking about low-level memory management issues. It's a type of automatic memory management, and it serves two main things: fast allocations and efficient reclamation of memory that is no longer in use. The fast allocation part is handled more or less the same, regardless of the GC algorithm you're using. So we have something called TLABs, thread local allocation buffers. These are handed out by the garbage collector to the allocating Java thread. And the Java threads can then do very fast pointer bumping allocations without any synchronization with other threads. When the TLABs are full, they are handed back to the GC and they get a new one. What differs between the different garbage collectors is how the efficient reclamation is implemented. And depending on how we implement this, the garbage collectors get different characteristics. The reason for having multiple garbage collectors is that the Java platform needs to serve a lot of different use cases. We need to be able to handle batch processing, UI applications, or cloud services. Big ones, small ones. Well, basically anything that you can imagine, the Java platform needs to support. And having a single garbage collector that handles all those use cases in a good way is very, very hard. Let's look a bit closer at how we do the memory reclamation part. First, we need to determine liveness. And what we mean by that is we need to figure out which objects need to be kept alive for the Java application to continue running properly. We do this by tracing the object graph, starting off with a well-known set of root objects. These are objects we know must be kept alive, like objects on thread stacks, static fields and classes, and a bunch of other things. When we have those root objects, we can follow references in those objects to other objects, knowing those must be kept alive as well. It's then time to reclaim the unused memory, and there are a set of different techniques here that you can use. For example, you can keep free lists, knowing here's free memory that I can reuse for allocations. Or we can do something called copying or compaction, where we move the live objects to a new location, making it possible to reclaim all memory in the initial allocation region where we allocated the objects. Then, depending on how you implement this, when you implement this, if you do it in a GC pause, stopping the Java threads, or if you do it concurrently with the Java application, that will give the different GCs different characteristics. And they will be differently good for different use cases. One of the most important things is, of course, to make this efficient. And there are, again, a set of different techniques that we can use to make it as efficient as possible. One of those techniques are generational collections. And what we mean by that is that we divide the heap into two generations. The young generation, where we place newly allocated objects, and an old generation to which we promote objects that have been around for a long period of time. The reasoning behind this is something called the generational hypothesis, which basically says that most objects are only used for a short period of time. And if this holds, we make use of it and saying that in the young generation, most objects will not be live, which makes it cheap to collect the young generation. And some objects will be long-lived and stay around. We promote them to the old generation. And at some point, we need to collect that as well, but much more seldomly. So now you know a bit more about how garbage collection works. But what might be more interesting to you is knowing which of the different garbage collection alternatives should you use for your application. And to know that, you need to figure out what's most important to you. And in many cases, we talk about 3 different aspects here. The first being throughput. Do you care mostly about throughput? And what we mean by that is the number of transactions that you can complete in a set amount of time. Then we also have latency, which is more about a single transaction. Is that affected by, say, for example, a GC pause? The latency can be bad, and the transaction can take a long time. And then we have footprint, the overhead caused by the GC algorithm. It's very hard to optimize for all of these at once. So usually we have to do a lot of trade-offs. If we try to illustrate a trade-off, it can look something like this. We have a set of application threads. At some point, we realize we need to do garbage collection work. We do this in a GC pause using multiple threads, trying to make sure that the GC pause is as short as possible before letting the application threads run again. This is pretty good from a throughput perspective, because when the application threads run, no GC work is going on. So they don't have to compete for CPU resources. On the other hand, from a latency point of view, it's not optimal because we have the GC pauses and they take a significant amount of time. So if we care more about latency, we can have something that looks a bit more like this. So again, we have the application threads, but when we realize we need to do garbage collection work, instead we do a very short GC pause, and instead do the heavy GC work concurrently with the Java application threads running. So from a throughput perspective, this might be a little bit worse because the GC threads and the application threads compete for the same resources. On the other hand, latency-wise, it's much better because the GC pauses are much, much shorter. In OpenJDK today, we have 5 different garbage collectors. We have Serial, which has a main focus on low memory overhead. We have Parallel, which is a throughput collector, aiming to provide as good throughput as possible. We have JavaOne, or the garbage first collector, which has a balanced performance profile. And then we have CGC and Shenandoah, which both aim at providing good low latency alternatives for Java. At Oracle, we maintain 4 of those: Serial, Parallel, JavaOne, and CGC. And those are the collectors that I will be focusing on for the rest of this presentation. So let's take a closer look at the different garbage collector alternatives. First, we have the Serial collector. Its main feature is that it has very low additional native memory overhead, so it doesn't use much more than the Java heap that you give it. It supports generational collections, and the heap layout look a bit simplified like this. So you have a young generation and an old generation. The sizes of those are decided upon startup, so it's not a very flexible heap layout, but it still supports generational collections, and that's very important. Serial just use a single thread doing the garbage collection work. So if you have a large heap size, it's not very optimal. The GC pauses will be quite long. On the other hand, you might be running in a small container, and then this might be a suitable alternative because you only have a single CPU available. So Serial is often a really good choice for small containers. Next, we have the Parallel collector. As I mentioned, it strives to provide the best possible throughput for the Java platform. It's also supporting generational collections, and the heap layout is very similar to the one of Serial. So again, we have a young and old generation with fixed generation sizes decided upon startup. The big difference between Serial and Parallel is that the Parallel collector uses multiple threads doing the garbage collection work inside the GC pause. And you might recognize this illustration from earlier, so this is really how we illustrate a throughput collector. The big problem here, or one problem with Parallel, is that if eventually the old generation fill up, we will have to collect the whole heap, the young and old generation, in one single GC pause. And this might inflict pretty bad worst-case latencies for applications using the parallel collector. Parallel was the default collector up until JDK 8, so anything running on JDK 8 or earlier, and you don't specify a specific GC, will likely use the parallel collector. Next, we have the garbage first collector, or JWone as we usually call it. I mentioned earlier that it's a balanced performance profile, trying to provide as good throughput as parallel, but with a way to avoid the worst-case latencies. And JWone have two features to avoid the worst-case latencies. First, JWone is region-based. So instead of dividing the heap into a young and old generation, JWone divides the heap into evenly sized regions. Those regions can then either belong to the young generation or the old generation, or of course be free if they're not used right now. Then JWone also supports concurrent marking. And concurrent marking means that we can determine the liveness information of the old generation concurrently with the Java application running. So looking at this illustration, you see that it's similar to parallel, but we do some work concurrently with the Java application threads running. When we have those two features, the concurrent marking, concurrent marking and region-based heap layout, we can do something called mixed collections. Those collections collect the young generation and a set of old generation regions in a GC pause. And doing multiple mixed collections in a row, we're able to collect the whole old generation without doing it in a single pause. We also worked very hard on making JWone as easy as possible to use. We have a single tuning knob that we mainly use, which is the pause time goal. The default value of this is 200 milliseconds, meaning that by default, JWone strive to have pauses shorter than 200 milliseconds. If you want JWone to have better latency, you can turn this value down, but if you want JWone to perform better from a throughput perspective, you can turn it up. JWone was made the default collector in JDK 9, so anything running on a more recent JDK is likely to use JWone, unless you specify a specific GC. Then we have the C garbage collector, or CGC. It's aiming on having very low latency and being scalable. To put this in perspective, we want the pause times to be below 1 millisecond, and it should be able to handle terabyte-sized heaps. So even if the sizes of the heap are really large, the pauses should be really short. Similar to JWone, the heap layout is region-based, and it's also as flexible as the JWone heap layout. The big difference is that CGC does all the heavy GC work concurrently with the Java application running. So they still have GC pauses, as you can see, but those are very, very short, and all the heavy work is done concurrently with the Java application threads running. The reason for still having GC pauses is that we need to synchronize between the application threads and GC threads to decide upon which phase we're currently in. Are we marking objects, gathering liveness information, or are we moving around objects, freeing up memory? When you have a concurrent collector, it's extremely important to make sure that the concurrency overhead is low, so that it's cheap to figure out if you can use an object right now, or if some garbage collection work needs to be done first. CGC has some really cool features to support this, such as colored pointers, and CGC has very, very low concurrency overhead. We added support for generational collections to CGC in JDK 21. In JDK 21, you still need to enable the generational support by using a flag called cGenerational. Since JDK 23, the default mode using CGC is the generational mode. So after JDK 23, you don't need to specify this flag. And yeah, we really encourage people to use the generational mode. So a quick overview of the different collectors. We have the serial collector, low overhead, suitable for small containers, parallel, great throughput, suitable for workloads where worst-case latencies are acceptable. Then we have JWone, good throughput, controllable latency, and suitable for long-lived services. CGC, good throughput, ultra-low latency, and suitable for long-lived workloads. So JavaOne and CGC seem pretty similar here. And if you care about latency, I really encourage you to try both JavaOne and CGC. Like a general rule of thumb is that the smaller the heap size is, the more likely it is that JavaOne is the right alternative. And on the other side, the larger the heap you have, the more likely it is that CGC is the collector for you. But always try at least 2 collectors. So this concludes the general introduction to garbage collection. And sorry. For the rest of this presentation, we will be focusing on performance. So looking at the benefits that you can expect when upgrading past JDK 8. JDK 8 was released over 10 years ago, and there have been some really significant additions to the Java platform since then, both in terms of functionality, like the virtual threads introduced by Project Loom, but also in terms of performance. And that's what I'm going to focus on for the rest of this presentation. The performance gains that we do see are not only due to changes in garbage collection, but changes to the whole platform. And we do see impressive improvements across the platform. The JDK libraries are improved, much more efficient today. The Git compilation produces more and better efficient code. And of course, the garbage collectors have become much better. If we zoom in on garbage collection, because that's what I care mostly about, we see some really impressive improvements across all different aspects of GC. We have better overall throughput, mainly because we spend less time doing GC work, so we can increase the throughput that way. The latency impact has been significantly reduced, again, because we spend less time doing GC work in the process, but also because we added low latency alternatives to the Java platform. The native memory consumption for most of the GCs have been cut down significantly, so the overhead of using GC has become much smaller. I said previously that it's very hard to optimize all aspects, and the way we've been able to improve all those different areas is that we've come up with better trade-offs than we did in the past. So we still have to do trade-offs, it's just that the trade-offs we do today are much more efficient than the ones we did back in JDK 8. So this is some general information about performance. Let's look at some performance numbers. And here I'm using the well-known benchmark spec JBB 2015. It's starting to get pretty old, but it's still a well-known benchmark for Java performance. It's good from a GC point of view because it provides 2 scores. It provides a maximum throughput score, which basically shows like all the performance benefits that you get from the platform, but then also a throughput with latency constraint score. I'm going to call that the latency score going forward. But this score takes the latency constraints into account. So basically, if you have long GC pauses, this score won't be good. I don't try to show which garbage collector is the best, because depending on the environment and other things, the different garbage collector perform differently good. But instead, I want to show the progress of each individual GC. So if we start looking at the throughput improvements, for JavaOne and Parallel, I'm comparing JDK 8, using that as a baseline, to 17 and 24. For CGC, we're using 17, 21, and 24, because CGC wasn't around in JDK 8, so we can't compare against that. And also for CGC, JDK 24 is the only release using the generational mode. So throughput-wise, for Parallel, we see some really great improvements. Going from 8 to 24, you can expect something like a 25 to 30% improvement in throughput. Going just to JDK 17, the improvement is somewhere around 20%. For JavaOne, very similar results, maybe slightly higher, but more or less in the same ballpark. And again, keep in mind here, this is not only due to GC improvements. This is improvements to the whole platform. For CGC, we can see that not much happened between JDK 17 and 21. And this is mainly because we focused all our efforts on enabling the generational mode of CGC, which was introduced into JDK 21, but here is shown as the bar for JDK 24. And as you can see, pretty significant improvement in throughput there using the generational mode of CGC. If we instead look at the latency score, and here is really where you can see the performance benefits of the things that we've done to GC. You can see that the latency score has improved more than 50% going from JDK 8 to JDK 17, or for parallel, more or less around 50%, and then slightly more going to JDK 24. For G1, the results are even greater, and we've seen almost a doubling in score going from JDK 8 to JDK 24. And still, the results are really, really good just going to JDK 17. And what we see here is basically the result of us cutting away so much of the work done in the GC process, or at least making it much more efficient. For CGC, again, the results are not as big, or the improvements are not as big. We should keep in mind that between 17 and 24, we have 3.5 years of development going on. So, and between 8 and 24, it's like 11 years. So the timelines are different here as well. Another reason for not seeing big improvements to the latency score with CGC is that the CGC pauses are so short that this latency score is very similar to the throughput score. So to be able to increase the latency score, we need to increase the throughput score. And to see this better, let's look at the pause times. What we're looking at here is the normalized P99 pauses. So still, I'm comparing the collectors individually. And if we look at parallel, we can see that we cut away about 40% of the GC pauses between 8 and 17, and a little bit more going to 24. For G1, we've cut away even more. One of the reasons for this is that G1 had slightly worse pauses in JDK 8, so we had more to improve on, but also because we spent a lot of time improving G1. For CGC, we do see that, do we have a regression here? Well, it could also be noise, because the CGC pauses are so short, we don't really have to care about them anymore. And to see this, let's look at the raw numbers. And please note that this is a logarithmic scale, because otherwise we wouldn't see the CGC numbers. And we can see that the CGC pauses are in the order of hundreds of microseconds. And the application latencies that we measure in this benchmark is in the order of 10 milliseconds for the latency score. So this is one of the reasons that the latency score is not really impacted by the GC pauses when using CGC. And this is true for many applications. Many applications using CGC doesn't really see the GC pauses causing any more latency than the application itself does. Looking at the G1 and parallel numbers, pretty impressive improvements, but in this kind of chart, it doesn't really show up. That's why I had the normalized chart before. But cutting down the pauses to around 80 milliseconds for both G1 and parallel is pretty impressive. The last chart I want to look at with SpecGVB is the peak native memory overhead. And we're using a 16 gigabyte heap here. So the native memory overhead is the additional memory that the GC algorithm has to use to be able to do its work. So for parallel, we can see that between 8 and 17, not much happened. It was very stable. But going to JDK 24, we cut away a significant part. And this was actually inspired by some work that we did in G1. We removed one of the marking bitmaps in parallel. And a marking bitmap is an internal data structure that we use to keep liveness information. And parallel had 2 of those. We came up with new solutions, only requiring to keep 1 of them. And yeah, a pretty significant save in native memory. Looking at the G1 numbers, we see even better reductions. I think going from 8 to 24, we've cut away the usage down to only like a third of the usage in JDK 8. And this was something that we heard a lot about in the JDK 8 timeframe for people using G1, that the native memory usage was way too high. The big reason behind this is an internal data structure called the remember sets. Those are needed to do mixed collections. But as you might remember, mixed collections are done to collect the old generation, and we don't collect that all the time. So we realized that we only need to have the remember sets when we collect the old generation. Being able to throw them away enable us to do these big savings. So we rebuild them when we need them, and that was a really great feature going into JDK 17, or between 8 and 17. Then between 17 and 24, we did even more efficiently efficiency improvements to the remember sets, but also cutting away one of JavaOne's marking bitmaps. Because JavaOne also had 2 of them, but nowadays only have 1. So pretty impressive improvements. Looking at CGC, it looks like the bar goes the wrong way, and well, it does. But the reason for this is supporting generational collections. You need to keep track of more metadata to be able to do this. CGC also needs remember sets. But the fact is that with generational CGC, you can support the same use case with a much smaller heap. So if you reduce the heap size, you can get away using generational CGC and still using way less memory compared to non-generational in most cases. So we don't see this as a big problem. Still, we do have ideas on how to reduce this going forward. This was the last chart using SpecJBB. So let's head over to the next application. Cassandra is a NoSQL database, distributed, well-known application with a very large user base. We use it in the Oracle GC team because it's nice to not only run benchmark, but using real-world workloads as well. And Cassandra highlights some really interesting aspects for us. So I have 2 charts here that I want to share. And we're looking at Cassandra using JDK 21 here. So now we're not comparing different releases, but we're looking at the actual performance using Cassandra. We're using a 32 gigabyte heap, or slightly smaller than 32 gigabytes, to allow JavaOne to use compressed hoops. On the y-axis, we're looking at the application latency, and on the x-axis, we have the number of clients. So we're increasing the clients and see how that affects the average latency. And if we're looking at non-generational CGC, kind of as expected, a linear increase. Same is through generational CGC, but slightly lower values. G1 and G1 with a 50 millisecond pause target. So that's the at 50 milliseconds means that I've configured G1 with a 50 millisecond pause target. And that is more or less the same results as with normal G1. And you might be surprised by this. Isn't CGC the low latency alternative? Well, looking at average latency is actually like looking at throughput metrics. So to see which garbage collector handles low latency the best, we should look at the worst case latencies. And that's what I'm having on the next slide here. As you can see, still the same chart, but the latency axis has much higher values. So the worst case latencies for non-generational CGC doesn't look very good. You might recognize this chart from the keynote, and you might know what's coming. But what I want to tell you about first is why we see this. And the thing that happens to CGC is that it runs into something called allocation stalls. When we add more than 75 clients, we start allocating too much, and the garbage collector can't keep up with the allocation pressure, and we run into allocation stalls. If you use CGC or generational CGC and run into allocation stalls, you really need to look at your configuration, either increasing the heap size or adding more concurrent workers to make sure CGC can complete its garbage collections in time. In this case, the thing you need to do is you need to run generational CGC. And seeing the worst case latencies with generational CGC makes a GC developer like me very, very happy. I'm pretty happy with what I'm seeing with G1 as well. We have the default pause target of 200 milliseconds, and G1 is keeping that for the worst case latencies, which is really good. And if we configure G1 with a lower pause target, we see that we're able to push the worst case latencies down. Not all the way down to 50 milliseconds for 275 clients, so still have some work to do there, but still pretty good results, I think. That was the last performance benchmark or internal numbers that I'm going to show. Now let's head over to some success stories from the real world. And let's revisit the company I mentioned during the introduction. I guess that many of you guessed that the company I'm mentioning or thinking about is Netflix. They have a very large stack of Java applications, and somewhere around 2020, they started upgrading to JDK 17. And they saw significant performance improvements. Most of their application on JDK 17 are using JWone, and they shared a chart using JWone, upgrading from JDK 8 using JWone to JDK 17 using JWone during this time frame. What we're seeing here is the brown line is the average pause time. The blue line is the time spent doing GC, and the gray area is that metric, but from last week, to make it easy to compare. And as you can see, the upgrade happening somewhere around July 8th, and pretty significant improvements there, cutting the pause time almost in half, and the time spent doing GC is also significantly down. But Netflix wasn't done here. In 2024, they started upgrading to JDK 21. And a big interest here was to evaluate generational CGC, see how that could help the worst-case latency that Netflix sometimes run into. And they were extremely happy with the results that they were seeing. And when having an application running in Netflix now, using JDK 21, by default, they are using generational CGC. They have written a really good blog post about this, and I picked a quote from this blog post that I want to share with you. Left unquestioned, assumptions and expectations could have caused us to miss one of the most impactful changes we made to our operational defaults in a decade. We'd encourage you to try generational CGC for yourself. It might surprise you as much as it surprised us. And the surprise Danny Thomas is talking about here is the fact that generational CGC works so well for all different types of workloads, all different types of heap sizes, because their expectation was that CGC would only be suitable for really large heap sizes, but that wasn't true. So we should always challenge our expectations, and we should always try out more than one GC, at least for use cases we don't expect them to work well on. Another company that is very happy with the results they're seeing going to a newer JDK release is Mercado Libre. They are the largest e-commerce, fintech, and logistics company in Latin America, present in 18 countries with over 120 million active users. They have a lot of microservices, and more than 8,000 of them are using Java. And many of them are now in the process of upgrading to use JDK 21. For them, the big drivers here, again, is generational CGC, but also virtual threads coming out of Project Loom. By adopting virtual threads, they were able to reduce the CPU usage by 15% and the memory usage with 20%. So really, really good results from adopting virtual threads. The initial results they saw with generational CGC was also really good, but they also noticed that CGC or generational CGC is using slightly more native memory, similar to what we saw here earlier. So they are still using JWone, but still evaluating if they can move and use CGC. Still, the results with JWone are good enough for them right now. They also wrote a blog post, and here's a quote from that one. The lighter virtual threads model optimized the handling of short tasks, reducing the impact on garbage collection and improving responsiveness in concurrent operations. The reason I want to highlight this is the fact that making use of new Java features can also give you a lot of benefits. And we can have synergy effects, like the virtual threads using less memory also helps the GC. And the GCs have become better, so you get like a double boost here. So yeah, you can upgrade and get free performance, but you can also make use of new Java features and see even bigger improvements. Another big company, also very happy with what is even upgrading to a new release, is LinkedIn. And they are upgrading to JDK 21. They also see generational CGC as one of the big drivers behind this. They have this big system called follow feed, which uses a very large heap. Back in the day, in JDK 11, they were using CMS. There were problems when using CMS as well, but it worked for them. They had worked around some of the problems. When upgrading to JDK 17, they still saw some problems with JWone, because in JDK 17, they could no longer use CMS because we remove that garbage collector. But there was a solution to this. In JDK 21, we have generational CGC, and the results they see with generational CGC there are really, really good. They see a 50% reduction in P99.9 latencies. So really nice to see that from yet another company in the real world. The last company or the last real world case I want to share with you is from the Oracle Cloud. The object storage team there, alongside a lot of the other services, are upgrading to more recent JDKs to benefit and get better performance by doing so. The object storage is mainly a throughput workload, but they do care about the time to first byte. So JavaOne provides a really good balance here between latency and throughput. And going from 8 to 17, they see like a 20% improvement in throughput, and the results look really, really great. They also shared a chart here. What we're looking at here is similar to the thing we saw from Netflix. So we're looking at the time spent doing GC. And it's pretty clear where the switch to JDK 17 happened. And after that, we see a significant reduction in time spent doing GC. So a few words about the future. We, of course, want to continue to improve. And we want to improve all the different aspects of GC. When it comes to performance, we have some really cool ideas lined up for JavaOne, trying to improve the barriers for JavaOne, making the difference in throughput way less between JavaOne and parallel. We also have some really cool ideas for CGC, trying to make sure that we can use CGC for even more workloads, allowing them to enjoy all the low latencies that CGC or generational CGC provides. We also want to keep reducing the overhead, cutting away the memory usage in CGC, but also enabling automatic heap sizing, making so that you as users don't have to configure as much, and making sure that we use an optimal heap size. If this sounds interesting, you should really listen to my colleague Eric, which is talking here in this room in like 20 minutes. He will be talking more about that. I also think it's very important to stay informed. And here is a set of resources that I encourage you to check out. So we have the GC tuning guide. It's updated for every release. So you just switch out the 21 there to 24, and you get the latest version. We have the developer portal at dev.java. Of course, also the newly released learn.java. If you want news and views from the Java teams, we have inside.java, where blog posts, videos, and other things from the Java team are posted. If you're interested in joining the development of the JDK, there are a lot of different mailing lists available on OpenJDK that might suit the area of your expertise or interest. So go there and sign up if you're interested in that. The code is open source, so you can find it out on GitHub, see the latest changes there, or do changes yourself. And of course, we're present on all the social media platforms. So the key takeaways from this presentation. There have been massive improvements since JDK 8. And if you have the opportunity to upgrade, if you're still on JDK 8, I really encourage you to do so. Also, choose your GC wisely. Depending on your use case, the GC you're using can really affect the performance, both good and bad. So really make sure you use the collector most suitable for your workload. And then last, keep on upgrading. Once you move past JDK 8, upgrading to a new release is often not that hard, and you can enjoy all the new things that we do to the Java platform. Thank you for listening, and I think we have like 5 minutes for questions, so please use the mics if you have any questions.
Hi.
Hi.
Anecdotally, sometimes it seems hard to find guidance for kind of small heap environments. So we operate, microservices with like 1 to 4 gigs of heap, 1 to 4 cores.
Yes.
But we're running online transaction processing workloads that are sensitive to pause times.
Sure.
And so kind of the questions are, how small is too small for ZGC? And are there, any specific guidance that you would have for people in a situation like ours?
So question is mainly if there is too small of a heap size for CGC to handle. The first question. So we don't have like a limit that we say this is too small, but generally, if you have like a high allocation pressure and you push the heap sizes down, CGC might run into trouble, like the allocation stalls I mentioned. But if you only care about latency, but you don't have that high of an allocation pressure, in many cases, CGC is able to handle that. Again, since CGC is a concurrent collector, it will be using concurrent threads. So if you have very few CPUs, that can also be problematic. What was the other part of the question?
Just if you had any sort of general guidance for people like sensitive to pause times, but operating kind of resource constrained.
Yeah, I mean, it's a hard problem to solve. And as I mentioned, always try out both CGC. Don't expect that CGC won't work just because it's a small heap size and those kind of constraints. But usually, the smaller heap size grows, JWONE might be better suited to handle those use cases. But please try out, and generational CGC is in most cases much more efficient in those kind of workloads. So if you have the possibility to use 21 and generational CGC, I think that's a good choice for you.
Thank you.
Welcome. Any more? Yeah, cool.
Maybe this is a dumb question, but do you
There
see
are
a
no
world?
such dumb.
Do you see a world where we're going to get to like near zero, like stop the world garbage collection?
I mean, I would say with generational CGC, we're near zero. Like the stop the world collect, like the GC pauses in CGC are in many cases neglectable. I mean, there are other things that can cause longer stoppages, like when you do an allocation, that could take longer time because there are some synchronizations going on and things like that. So the GC pauses in CGC, as you saw, like the worst case pauses with generational CGC on the 16 gigabyte heap and on basically any heap size, because the pauses don't grow with the heap size, are in the realms of hundreds of microseconds. Again, depending on what kind of application you have, hundreds of microseconds might be a problem. We have ideas on how to reduce these, maybe a little bit more, but I'm not going to say that we never will go away from any GC pauses, but right now we have other things to focus on.
Thank you.
Cool. Again, thanks for listening. Hope you learned something, and go do GC.